How's it going, everyone? Welcome, Euler Gonzalez here, explaining and looking and exploring the functional light JavaScript. So, why we are actually doing this? Well, as a way to now look at this mathematical tool, pretty much when you go on to pay a bill, restaurant bill. So you don't need to know is the mathematical proof that 1 plus 1 is equal to, or about the addition, subtraction, multiplication, and division. You just only know that what is the input and what is the output that this stuff give you, and that's all, right? So this is pretty much why we're looking at the functional programming, which is a course taught by Kyle Simpson. Shout out to Kyle Simpson. He explained now is the mathematical tools that we can use now as a way to write applications that when we look at them, we can rest assured on the mathematical bedrock, mathematical foundation, prove that work as expected. So it gives us is predictability of that this stuff is working as it is, right? So instead of focusing our attentions on stuff that are irrelevant, so the value proposition of this is that wouldn't be nice to have a code where 80% of that will be mathematical proof that we can rest assured that it work as expected, so we can only focus on what's critical and what's really important, that is the business logic. So that's the entire reason of looking at this. And as a byproduct, you of course will gonna have is a self-documented code, a code that is provable, that it will behave in a predictable way. All right. And now, what are the tools that we can go with, or that we need to know as a way to apply that in our code? So first things first, we went through describe is about the functional programming, that unlike the imperative programming, which is something that we are get used to write code on this. So unlike other courses out there where you now have this top bottom approach, Kyle Simpson say, hey, let's go to now go with this bottom top approach. In other words, with what you already know, that is imperative programming, and then move on to what we really care, and that is functional approach, and how you can write that, so on and so forth. Now, so that's why we first look at functions. So what is the difference between a function and a procedure? And at the end of the day, a function, which is something that takes an input and give you an output, unlike a procedure, which is a set of steps that doesn't return anything and also cause side effects. It can modify the state of the outer code. Now, by looking at the relationship between the inputs and the outputs on the function, this is how you can now give a name to what this function is. And as a way to have this provability that our code behave as expected from the functional approach, and don't water it down by doing stuff that are not aligned to the functional programming, one of them is that this particular function, which is the relationship between the inputs and the computer output, now that function should not cause side effects. In other words, should not affect the outside world that it lives in, that is inside of this code. So eventually at some point we need to handle this kind of stuff, all right? Known as dealing with input and output operations, reading to a database or to a local files, or waiting for a response to waiting for a message to arrive, waiting for incoming message, also accessing the DOM, generating random numbers, and all of this will ultimately now generate a CPU heat, okay? And that particular aspect was quite interesting. All of this generated CPU heat and CPU time delay, right? So anything that ultimately generate CPU heat, so it takes time to process. That makes a lot of sense. So anything that, so you can boil down to anything that generates CPU heat, it takes time to process, or CPU time delay, you need to wait for something, are considered side effects, right? And that's quite interesting if you truly boil down, at least for the computer aspect. So that's why we look at the function purity. What a pure function means is that it doesn't have side effects. But what happened with at some points or in our program we need to handle with this impurity, these side effects. So how can we now extract the impurity in our functions? And what are the techniques to do that? One of them is to take the so one of them is extracting. So this is explaining is now why pure function is important, and not only for the side effects, but also for the way that it now reduces the surface area in which a input can be reassigned. And that gave us, of course, much more certainty that this function worked as expected. So what happened when you, because at the end of the day with the function purity, it's just increase the level of confidence. But for the function caller of that function, right? So yeah, despite that the function definition has to follow certain guidelines, but the point of this of function purity is that anytime we call that function, we got an expected outcome, period. So what happened when we don't have pure functions? So how can we now make those pure functions to work with? All right. So one of them is extracting impurity. Okay. And the extracting impurity technique is by extracting impurity or containing impurity. The extracting impurity is to say, hey, it's going to create a function that generates a new state of that, or the containing impurity, which is something that we did in a particular exercise, is to say, let's going to now take snapshots of everything that this function needs and then return the function as expected. Or return, exactly. Or return now the state that has been modified in a pure way, right? So by recreating is a new state. So there was a couple exercises there that we work on that. So if you say, for example, on our GitHub here, let's see this one. For example, this, right? When we say here with impurity, right? So wrapping a function to contain the impurity, this is something that we are quite familiar with. So for example, if that function that is performing a side effects, aka is generating CPU hits, or is the CPU times delayed, generate CPU time delayed, okay? So in our case is this function that actually are computing that, is sorting that. What we can do here is to say, you know what, let's go to now wrap this function, okay, or contain the impurity by wrapping these functions with a state that we capture that'll be used inside of this function. And that's it. And this is interesting because here what you're doing is just creating a copy of this data that's going to be mutated, but encapsulating it. This is the more straightforward solution when you need to apply this kind of impurity here in your code, right? So for example, it's like, hey, how can we, for example, exactly. So at this moment, this function is now sorting, or doing any doing tasks that generate CPU hits. Okay, so any high CPU intense task, all right, or that generate times delayed. All right, so one way to extract the impurity of a function is by wrapping around that into a function that is going to capture the state, and therefore at that scope is going to now work on that. This is pretty interesting here. This is pretty interesting, at least in this case. All right, at least in this case. So what you're doing is just to create a new copy of this reference and work with this reference and work with this new copy so you can apply the transformation and returning. There's a lot of things going on here, in terms of how you can describe that. So far, so good. The other technique, which might be it requires several kind of steps, which is, this is known as containing the lexical scope technique. So you are containing the lexical scope techniques. And now what we're doing is the brute force technique, which is generating adapters. But in other words, it's like taking the entire state of that application, okay? So taking the entire state of that data and in the new data that you're going to receive, so you can now apply that transformation and then reset the state to the original state as you get it, right? So eventually here what it's doing is to take the current snapshot of everything and then restore it afterwards. That's mind-bending stuff. That's definitely mind-bending stuff. That's definitely mind-bending stuff. All right. So. What are we gonna talk about in today's video? Glad you asked. If you do, if you're not, no problem. So this is now extracting impurity and containing impurity as it is. So wrapping a function to contain impurity and extracting impurity via adapters. Let's going to actually double check this.
Okay, let's talk about the solution for part 2 of the impurity exercise. What we said was we want to take this get students by ID and make it as an adapter function to the sort students by ID so that it will contain, if you will, it will prevent from leaking out any of the side effects that the sort students by ID would have.
Because at the end of the day, you're containing as well. You are containing. So exercise. Containing impurity. Containing impurity. Via, exactly, containing impurity containing impurity by taking the lexical scope of that, or copying, exactly, containing impurity by holding, exactly, extract function impurity. The goal is to extract function impurity, since the idea is from the color perspective that this function behave predictable. So containing the lexical scope technique and return a new copy of that, So containing impurity by containing the lexical scope and return a new copy of that. Okay, pretty straightforward. And the other is exercise. This is technique exercise. It's containing that. It's containing that. Extracting impurity via adapters. Exactly. The other is technique exercise. Extracting impurities via adapters. Or another word is to via adapters. Just take a snapshot of everything. Okay, take a snapshot of everything, and then compute that, and then restore it afterward. Oh, take a snapshot of everything, and then restore it afterwards. That's interesting. So it makes quite sense because, again, the TLDR of this function purity is that from the function color perspective, you're going to get that without side effect in a predictable way. So now, let's go into now explore about is the arguments and adapters. Arguments, adapters. It's the arguments, adapters. So arguments, adapters. That's right.
Let's shift our attention, we're still talking about functions, but let's shift our attention specifically to the arguments, the parameters that functions receive. And by the way, just to clear up some terminology, parameter and argument are often used interchangeably. They are technically different.
So arguments and parameters are using interchangeable. But they are technically different. And here, this is what we're going to look at today's video. Functions, arguments. So functions, arguments. There you go.
The generally accepted definition here is that a parameter is the thing in the function definition. Like if I say function add number, and then I have x and y. The x and the y are parameters. What is an argument then? That's the value, add number, and then I have the generally accepted definition here is that a parameter is the thing in the function definition. Like if I say function
Okay. So parameters are the reference. Okay. Parameters are from the function definition point of view. POV. All right.
Add number, and then I have x and y. The x and the y are parameters. What is an argument then? That's the value that gets passed in when you call the function.
Parameters are the name inputs from the function definition. So for example, x and y to calculate is the area. No? Or to calculate the sum of two numbers. So just you get a function here, sum, say x and y. X and y, and then you say, hey, let's go to return is the x plus y. Pretty straightforward, basic stuff, nothing too fancy. This one.
So if I later I are parameters. What is an argument then? That's the value that gets passed in when you call the function.
That's right. So an argument is the value passed in when we call a function. This two stuff are important too. Arguments are the value that we pass to a function when we call it. And arguments is the name reference inside of the name input reference inside of the function's definition.
So if I later say add number 3, 4, the 3 and the 4 are the arguments that get assigned to the parameters x and y respectively. Arguments get assigned to parameters.
Exactly.
So when I use
Values are
arguments
assigned
here,
to
I'm referring to
parameters.
the...
So arguments are assigned to parameters.
The things that are being passed in, but we also are encompassing in that umbrella the parameters that they get assigned. We're talking about the inputs to the function. We want to look at the nature of the inputs of those functions. All right, so if I have a function called increment that takes a single input value, in this case x, and it returns a value back, in this case it's the sum of x and y, there's a special term to describe that shape of function. And I'm going to use this idea of shape throughout the rest of this course. Okay? And I want you to understand, I could be talking about things that are much more formal, like type definitions. But I don't think that's useful for us, so I'm going to use more informal language here to describe the shape of a function. Okay? And here's what the shape of a function is. The number and the kinds of things you pass into it, as well as the number and the kinds of things that come out of it. That's the shape of a function. Being less formal than restricting ourselves to some particular type language. Okay? Talk about type signature. So the shape of a function that takes a single
So the shape of a function he's talking about here.
I could be talking about things that are much more formal, like type definitions. That shape, and it returns a value back. In this case, it's the sum of x and y. There's a special term to describe that shape of function.
So there is a formal way to describe the shape of a function, which is the type definition.
And I'm going to use this idea of shape throughout the rest of this course. Okay? And I want you to understand, I could be talking about things that are much more formal, like type definitions.
Mm-hmm. So this is a formal way. There is a formal way to describe the shape of a function. So what are the inputs it receives and the output it generates, right? So what are the inputs? So what are the inputs it receives and the outputs it generates, right? Okay. Yeah, there is a formal way to describe the shape of a function. So what are the inputs it receives and the outputs it generates? Called type definitions. Formal like type definition, and that's okay. That's why it makes a lot of sense with this type. So anytime we talk about types in functional programming, we refer is to the shape of the function, the inputs that it takes and the outputs that it generates. So why?
But I don't think that's useful for us, so I'm going to use more informal language here to describe the shape of a function. Okay? And here's what the shape of a function is. The number and the kinds of things you pass into it.
So there is a formal way to describe the shape of a function. So the numbers and the kind of thing you pass it. The number and the kind of things you pass in, as well as the number of this kind of stuff that come out of it. So the number and the kind of thing that you pass in, and the number and kind of things you come out of this. That come out. That came out of it. But here is part of the shape of the function. Is the number and the argument is the number and the shape of the stuff that you pass in, and the shapes and the number and the kind of stuff that come out of this. That come out of it.
That's the shape of a function. Being less formal than restricting ourselves to some particular type language. Okay? Talk about type signature. So the shape of
type signatures. So type signatures is what is the shape of a function. And this is what we need to start from the concept, from the basics. Oh, these type signatures, okay, type signatures are like that. Makes a ton of sense.
Of a function that takes a single value in and gives us a single value out, that shape has a special kind of name. We call it a unary function. And if we look on line 7 at a function called sum, that takes an x and a y, that has x and y formal parameters. That takes 2 inputs. So the shape of that function is a little different. It takes 2 inputs, still returns 1 output. We call it a binary function. So we have terms, unary and binary. They could sound scary, but they're actually pretty straightforward. They're just describing the shape of the input signature.
So here the describing is the input signature, or the output, the input and the output signature.
What do we expect to be able to pass in? And importantly, what do we expect to be able to get out? And it turns out that the shape of functions is super critical. The functional programmer is almost obsessed with the shape of functions. Very similar to if you were playing with a set of Legos and you were trying to build up a model, it would matter if this piece fit on top of this piece, wouldn't it? If they didn't fit, you couldn't use them together. So if I have a bunch of functions in my application and their shapes are not compatible, they don't fit, like Lego pieces don't fit, then they're not going to work together, are they? The shapes of our functions matter. And it matters so much that in the authoring of our functions, we're constantly thinking, what is this shape going to imply to my future usage of it? Am I going to restrict myself to only using it in certain cases if it looks like this? For functions that we are in control of, we want to care about the shape. When I say in control, I mean we get to decide the design of the function, like what it's called and what it takes and what it returns. For functions that we decide, we want to be very cognizant of that shape and what it will imply, what it will create as an effect when it's being used. For reasons that you won't fully understand now, but you will begin to get as we go further along. Functional programmers tend to prefer unary functions. Single input, single output. And
so functional programmers are obsessed with the shape of a function, since this is critical to fit each one into another. Pretty much like Lego blocks when you are trying to fit one piece with another to build a spacecraft. Okay, so functional programmers tends to appreciate or tends to use unary functions.
their next favorite kind of function is
their next kind favorite function. Functional programming tends to use unity function, and their next kind favorite function is binary function. Is binary functions.
Is a binary function, 2 inputs, single output. And I'd say probably 95, 98% of all functions you'll ever see in a good functional program will be of one of those two sorts.
One input, single output is a binary function. 2 inputs, 1 output here.
It's probably like 70-30 unary versus binary. There is a term to describe all the other functions, those miscellaneous ones that take 3, 4, 10, 20, whatever. We call those n-ary functions. They're vastly less common because the more inputs a function has, the harder it is to make it work with other functions. The harder it is to get the shapes to fit.
So the more a function receives arguments, the more harder is to make it fit to work with others. But again, functions argument here, argument adapters. Functions argument, especially here, of the shape of the function is focused on the number of kind of things that you pass, the number and the shape of things that you pass here, and the number and shape of things that come out of it. Yeah, of stuff that come out of it.
We can also adapt the shape of functions. And this is where we're going to really start to push your thinking around functional programming. Because we're going to introduce a concept. I'm sure many of you have heard this before and maybe just didn't fully connect with what it meant. Have you heard the term before, higher order function? Sometimes it's abbreviated HOF, H-O-F. Okay? So what is a HOF? Sounds much more complicated than it actually is.
It's a function that
That's the
takes
cool part,
another
is that when we have
function. It's a
these
function that
meetings,
takes
a lot
another
of
set of
stuff is actually pretty
instructions as an argument.
Not always, but some of it. So what is a higher order function? Well, put simply, a higher order function is a function that either receives as its inputs one or more functions, or returns one or more functions. That is, if the values going in or the values coming out are functions, then that thing itself is the higher order function. So a thing that doesn't receive functions, we would call it a single order function. And if it receives functions or returns them, we call it a higher order function. Okay? So right on line 1, we see a utility that I've now called unary. You see that it receives a function denoted by the parameter. The values going in, one or more functions, or returns one or more functions. That is, if the values going in or the values coming out are functions, then that thing itself is the higher order function. So a thing that doesn't receive functions, we would call it a single order function. And if it receives functions or returns them, we call it
function.
a higher order function.
Higher order function.
Okay? So right on line 1, we see a utility that I've now called unary. You see that it receives a function denoted by the parameter fn, and it returns another function back called 1 in this case. That's called a higher order function. The unary utility here is a higher order function. What is it doing? Well, it's kind of interesting because that one function that gets returned back, it only has one named parameter. You may be or may not be aware that in JavaScript, all functions are what we call variadic, meaning it doesn't matter how many parameters are declared, you can pass as many arguments or as few as you want. You can define a function that expects 3 and you can pass 4 to it. You can define a function that expects 3 and only pass 1 to it. JavaScript's not going to say, you're doing something wrong. They're variadic functions. So if I were to take a function that might expect 4 and pass it, like, for example, the f from line 13, one that expects multiples, it's an n-ary function. But if I pass it to unary, what I get back, line 17, g is a new function, which has the name 1 that we see there on line 2. G, down on line 20, when we pass in 4 inputs, how many inputs actually make it to the underlying function? 1 that we see there on line 2. G, down on line 20, when we pass in 4 inputs, how many inputs actually make it to the underlying function? G, down to unary, what I get back, line 17, G is a new function, which has the name 1 that we see there on line 2. G, down on line 20, when we pass in 4 inputs, how many inputs actually make it to the underlying function?
Only one.
How many? Just 1. Because on line 2, we named just a single parameter arg. So in other words, we took a function whose shape was to be n-ary, and we reduced its shape, we restricted its shape, such that it is what?
1.
It's unary. That's what the unary utility does. It's a higher order function that adapts the shape of a function to be unary. We'll see use cases throughout the lecture and exercise where that kind of thing will be useful. But I want you to get more comfortable with the idea that a function of one shape can be adapted to have a different shape. That's critical. That's a key takeaway from this higher order functions pattern. Is that we can take any function and adapt its shape. And that's critical when we have 2 Lego pieces that don't fit, and we need to sort of make them fit. We've got to make an adapter so that they fit. And that's what these utilities do. In fact, virtually all the utilities that you'll find in whichever functional programming library you choose to use, RAM, Dolo, Dash, whatever, whichever one you pick, all of the utilities are these kinds of higher order functions. Almost all of them do this kind of thing.
It's because with this argument adapters, with the shapes of the function, which is the number of stuff in time, the number in time of stuff that it receives, and the number of kind of stuff that it came out of this is because now
sensible to you. Okay,
4
I take a
cents
function and make
unary
another function
function.
wrapped around it. And that's the key, because you as a functional programmer have to get comfortable with making your own higher order functions. Not just using the result of a higher order function that's provided to you, but making your own. When you see that I have this piece and they don't fit, the functional programmer says, I can see what kind of adapter I need between them, and I make myself a utility to do that. And then I create the shape-adjusted adapter. Make sense? So unary makes the G would be called the unary of F. Line 18 we call H equals the binary of F. So on line 21, when you see H receiving 4 arguments, the underlying function, the F function, only receives 2 of them. We've made it the binary. If you haven't dealt with higher order functions before, expect for that
Argument shape adapters. The reason of looking at the, you know, it's exactly, you're starting to mapping here. So the reason, oh my God. Oh. Exactly. So argument shape adapter. So the reason of understanding the so the reason of understanding the value. Okay, makes a lot of sense. Yeah, argument shape adapter. So the reason of understanding the value, the shape of a function is just to recognize the anatomy of a function, arguments, and it is adapters, okay, arguments and parameters, okay. So the reason of understanding the shape of a function is just to recognize the anatomy of a function, arguments and parameters, okay. So the reason of understanding the shape of a function is just to recognize the anatomy of a function, arguments and parameters, okay, and explore. Exactly. So the reason of understanding is the shape of a function is just to recognize the anatomy of a function, arguments and parameters, and to make it easy for us to create functions or functionality that is predictable, okay, and to make it easy for us to create functionality that is predictable, all right. To create functionality that is predictable, we need to also look at how can we fit one function with another. In other words, how can we make or how can we adapt, okay, in other words, how can we adapt the shape? How the fuck do you get in here, girl? Anyway, in other words, how can we adapt the shape of one function into another. Get the fuck out of here. Anyway, but it's
brain to feel a little, but this is critical. It's going to be core and central to all of your future functional programming. Let's look at some other kinds of adapters. Here's one called flip. It will sometimes be the case that you have a function, let's say you have a binary function, and it receives an x and a y. I don't know what it does, it doesn't matter. It's a function that receives an x and a y. And there's a bunch of places where that works just fine. But then there's this other place where you need a function that receives them in a different order. You need like yx. For whatever reason, you need to be able to provide the arguments in a different order. That's a new shape adaptation, right? And if it's a shape adaptation, then we can make an adapter to do that. And we call that adapter flip. Notice what flip does. It takes in a function, returns back a flipped function, line 2. It lists arg1 and arg2, and then it transposes them when it calls the underlying function on line 3. And everything else that's passed, if anything, is passed along untouched. But flip simply flips the first two. By the way, flip is the name that is canonically used in most libraries for exactly this function. It's called flip. Same with unary and binary. Wherever possible, I'm going to try to use whatever names you'll probably see out in the wild. Not always, but where possible. Okay? So you'll find a flip in there, and now you know what that does. And that's like learning about the plus operation in math. Because now that you know what that does, every time you see flip with an fn passed in, you know that the thing that's being passed back is transposed to it. And the job of becoming a functional programmer is getting comfortable with seeing all of these different mathematical pieces and saying, yep, this is the flip, and yep, this is the unary, and yep, this is the binary, and this is the this, and this is the dot. Seeing those and recognizing those at a glance and using them just like you use 1 + 1 = 2. When I make G on line 11, that is the flip of F. So when I pass in G 1, 2, 3, 4, the underlying F actually receives 2, 1, 3, 4. The first two arguments having been transposed. A somewhat less common example that you may find would be reverse Rs. That's a name that I made up, okay? Because this isn't one that you're going to find in all of your functional programming libraries, but it's one that I've often found useful. So I went and made my own higher order function utility, because sometimes I have like an n-ary function, 3 inputs, and I need them all 3 reversed, not just the first 2 flipped, but I need all 3 of them to go in reverse order. That's happened to me on a number of occasions. So what does reverse args do? Exactly what you expect. It takes a function and returns back a new function that takes the list of arguments line 2, and line 3 it reverses.
And reverse it.
That's an example of an adapter that I made that I might use. Not one you necessarily find, but it's an example when you find yourself messing around with the shape of your functions and they don't fit. Try to figure out, number one, can I change the shape of my function at definition so that it fits better? If not, can I make an adapter that changes the shape? Everywhere that we do this, we're looking for common patterns. The functional programmer is looking for the Lego piece that looks exactly like the Lego piece that they have a big old pile of. I want this thing to look like a Lego piece that I already have. I don't want to go invent new utilities all day, every day. Stop and think about that for a moment, because that may not be obvious. Why might I not want to just invent ad hoc utilities all over the place? Because, quite honestly, it's kind of creative and fun to do so. I can come up with all kinds of different shape-changing ones. Why wouldn't that be a good way of approaching my code base? And I would suggest to you that maybe why it's not such a great idea is because the whole point of being able to glance at something is the familiarity, the recognition of it. Wherever possible, if the things that we're using are the known common things that every functional programmer for the last 60-something years have used, that's good. But when a functional programmer comes to your code base and they see this thing and they're like, oh, what? I've never seen that Lego before. It's less familiar. So somebody has to spend more time reasoning about that math. Where it's possible for us to do so, we should try to make it recognizable. We should try to use the standard common ones. So that means get real familiar with at least one functional programming library and most of the methods that it provides. Once you've spent a few hours reading through the documentation for Lambda, for example, you're going to find yourself looking at a thing, seeing this shape and saying, oh, I know what that one's called. I saw that in the Lambda docs.
It's
Congratulations, that's functional programming. Instead of go invent your own and make one that isn't consistent and familiar, try to make it fit in with the existing patterns wherever possible. And when you can't, make your own. Document them well, put them in a standard library that the whole app uses, and use them as much as possible. That way everybody gets familiar with them.
exactly. Use as much as possible all of those.
Another
in this
example of
library.
shape adaptation that we commonly do. You will see this much more often than may be obvious at this moment. One kind of shape adaptation is I have a function that takes individual arguments, but I want to call that function with an array. It's expecting individual arguments, but here I have an array. What do I do? How do I get all the contents of this array into the individual arguments? Some of you may know about JavaScript's .apply method, which takes an array and spreads the values out as arguments.
Dot apply.
And there's a reason why that utility is called .apply, because that's what functional programmers call it. When you take an array and spread it out as individual arguments, that's called an apply. Here I've called it spread args, just so you knew exactly what it's doing. It's spreading the argument, the array of arguments out into individual ones. See how it does line 3, the ... That's the spread operator. It is
It is spreading the arguments that are passing to this function by the time that they call it. For example, function is spread arguments by this function. It say, hey, by the time I call this spread args, I'm gonna receive this function, and inside of this function, I'm gonna return now that this function that I'm receiving as a reference. Okay, exactly. And there's another function called spread, okay, that is going to return this another function, okay. So by the time that now we call this with the proper values here, part of the higher order function, by the time that we call the function that we return with this, with the arguments, we're going to have now is that function that we receive, and with, okay, that function that we initially receive, all right, and apply these arguments. And apply those arguments. Or in other words, is to take that function and spread the arguments that I'm going. Okay, so take the functionality and their values, and then do some computation from that. Take this functionality with these values, so you can do this stuff.
spreading out an array of arguments into individual. But that's exactly what JavaScript's .apply does, and it turns out the name for this utility, as you'll find it in almost all functional programming libraries, is apply. So the apply, G is the apply of F.
And apply and call is that apply is going to apply and call is going to both of them serve the same purpose, just that one of them accept is the argument as an array, and the other is as parameters. So call accept their arguments as a parameters, one after the other, and apply it as an array. Let me actually do if that is correct. And arguments provide as an array, like. Again, they're gonna call it, okay? Max will say, hey, apply to this function with this set of arguments here. Holy hell, bro. This is where now the start of the functional programming
That's what functional
comes.
programmers call it. When you take an array and spread it out as individual arguments, that's called an apply. Here I've called it spread args, just so you knew exactly what it's doing. It's spreading the argument, the array of arguments out into individual ones. See how it does line 3, the ... That's the spread operator. It is spreading out an array of arguments into individuals. But that's exactly what JavaScript.apply does, and it turns out the name for this utility, as you'll find it in almost all functional programming libraries, is apply. So the apply, G is the apply of F, line 11. It's the spread args that is the apply of F. So when I call G with an array, F gets individual arguments. Everybody follow me? Here's a little pop quiz. We're not going to actually show this code, but I just want you to play with this in your head, maybe type it in your code for just a moment. This is a pop quiz. If spread args is a function that can take an array and spread it out into individual ones, what's the inverse of that? What would unspread args look like? Unapply, what would that look like? I would be able to pass in individual
We'll be able
arguments.
to pass individual arguments here to this function, and then somehow is to summarize all of them into one argument.
Minutes. And the underlying function would receive what?
Array.
An array. Just think about that for just a moment. We'll just take like 30 seconds. That's the pop quiz I want you to think about. Look at that spread args and think, how would I change this to do the inverse? It's not as complex as you might have thought. The dot, dot, dot operator on line 3, we simply need to move it from line 3 to line 2. We need to gather the arguments from line 2 and pass them as a single array line 3. That's it. That's the only difference between a spread args and a gather args, or an apply and an unapply, is whether we gather first and then pass the array, or spread, and then, or take an array and then spread it. It's the only difference between the two. And you'll find apply and unapply in all your favorite functional programming languages.
Okay, so that'll be all for this video. Take care. Bye-bye.
All right, so let's take a look